Hello and welcome back, everybody. AP Chemistry. We're taking a look at Unit 4, Section 4, taking a look at acid and base reactions. And so we're going to be taking a look at a couple of basic definitions of acids and bases. And really with this, we want to keep in mind there's a couple of ways we can think of acids and bases, a couple different lenses, if you will, how we're going to be looking at them. So let's take a look at that part first. We can look at acids and bases through an Arrhenius lens. Okay, the Arrhenius lens means that if you're a hydrogen, it's going to produce a hydrogen ion in water. Okay, and if it's a base, it's going to produce, instead of a hydrogen ion, it's going to produce a hydroxide. So it's typically how we think of these things within acids and bases. We just see a hydrogen out in front, that's an acid. So an example of this, there's a couple of examples that we might see. Like, for example, hydrochloric acid. It's a combination of the hydrogen ion plus the chloride ion. Another example that we might find here would be something like nitric acid. HNO3. And we can think of that as the hydrogen ion plus the nitrate ion. Okay, so that's one way to think about it. And how this would work is if we end up with mixing this in water, we could think of this another way with hydrochloric acid. We could think of hydrochloric acid, when we mix it in with water, it's going to form what's called a hydronium ion, an H3O plus. It's just basically water that gets that extra hydrogen on there, and that would generate then the chloride ion. So it's another way of thinking of this. And similarly with, we're going to be doing that with the nitric acid. We would have water in here, and we get the hydronium ion with the nitrate ion. Okay, so that would be an example of some Arrhenius acids. Now, in the case of an Arrhenius base, we would take a look at sodium hydroxide, and that would dissociate in water into the sodium ion plus the hydroxide ion. So that's a basic definition within the Arrhenius lens. But if we take a look at a Bronsted-Lowry definition, however, we would think of any of these compounds, it behaves a little bit differently, as a proton donor. Now remember what protons are. A proton is a hydrogen ion in there. Okay, so I'll show you an example of what I mean by donor in just a second. And the base then, rather than being a hydroxide, a base would be anything that would accept the hydrogen ion. So let's take a look at an example of that. And let's use, for example, the hydrochloric acid in this case. And let's take a look at water and see what's actually happening. Again, I can think of hydrochloric acid as an Arrhenius, but let's take a look at what's going to happen in this reaction. I said that it's going to form the hydronium ion and the chloride ion. Now, what that means is the hydrogen off of hydrochloric would be donated into the water. So that would make this my acid, and that would make this my base. Now, if I was going to reverse the reaction, what would I have to do? I'd have to donate a hydrogen back in. And so this is on the product side, so this is what I would call my conjugate side. The conjugate acid, he would donate it back in to my conjugate base. Okay, because chlorine would take that back in. So acids, bases, conjugate acid, conjugate base. So that's an example there. Let's take a look at another example of the case where we have like hydrochloric acid and sodium hydroxide. Okay, what I'm going to get off of this is my hydrogen is going to go into my hydroxide. So he'd take it in. Here's my base. Here's my acid. And I'll end up with sodium chloride as well. Now, on this case, if I was going to reverse the reaction, what would have to happen? I'd have to give the hydrogen back into my chloride. So the hydrogen would go back in here. He would take it in. That would make this my conjugate base. Even though it's salt, it would behave like a base. And even though this is water, it's supposed to be neutral. He would act as an acid. Okay, so that's how that works. And so just in general terms, we have two different ways that we can be thinking of it, and it's especially useful for Bronsted-Lowry to be thinking that things that don't appear to be acidic or basic would actually take on those traits. Okay, so there is, and we're going to get into acids and bases a little bit more detailed later on, so let's just look at strong acids and strong bases. If it means that we have a strong acid, it means that it is going to give up lots of hydrogen ions. it's going to give up lots of hydrogen ions if it's a strong acid, or take in lots of hydrogen ions if it's a strong base. If it's weak, there's not going to be many that are going to be produced or taken in. Okay, they'll give it some, but not very much. Okay, so again, going back into this, what that means is within our flask, we see like sodium chloride. This is a +1. I'm going to get lots and lots and lots of hydroxides in there, and lots and lots and lots of hydrogens. That's in that example of hydrochloric acid. If I dump my hydrochloric acid in with my sodium hydroxide. Okay, so that's an example. I got lots and lots and lots of hydrogen ions. But here I have a case with a weak acid or base, and we're going to get into the mechanics of how this happens. I might put in something like acetic acid, commonly called vinegar, HC2H3O2. Okay, so what ends up happening if I mix that with my sodium hydroxide, I'm going to get just a couple of hydrogen ions floating around in there, not lots and lots. I'm going to get some sodiums in here that are going to dissociate, but I'm going to get lots of these just remaining behind inside. That's going to leave those negative ions floating around in the solution, since not many of the hydrogen ions will come off, and we're going to cover these later on in the unit. So just wanted you to see that reaction in general terms when we're talking about strong acids and strong bases. For now, we're just going to be taking a look at some strong acids and get into the other mechanics later on. Okay, so let's take a look at what we can do with problems like this. If I take a solution and I have a certain concentration of it, and there's an equation that can go in there, and I'm going to use the number of hydrogen ions that are going to be given up as a function of the molarity of the acid as well as the volume of the acid. And that volume can be in whatever units as long as it's consistent on both sides. And that will equal the number of hydroxide ions with the molarity of your strong base and the volume of that strong base. Okay, so let's pick apart this problem. I see that I've got in here, I'm going to be taking a look at a solution of hydrochloric acid and sodium hydroxide. But pulling apart this problem, what I'm doing is I'm putting in, using the burette, I'm putting in hydrochloric acid into this, and I'm going to be neutralizing my sodium hydroxide in here. My strength of my acid, the problem is telling me I have a 0.100 molar solution, and the question is, what's my volume? Okay, that's given within 25 milliliters of this. So let's take a look, and I see I have my volume right here, 25.0 milliliters. I see its strength is going to be 0.350 molar. And that portion, what I'm talking about with those, I see within sodium hydroxide, it has one hydroxide to give up and donate and play around with. Now on this side, I can see my hydrogen ions. It is hydrochloric acid, so there's only one hydrogen to play with. I see that its strength is a 0.100 molar. And so the question is, what's its volume? Since I was in milliliters here, let's go milliliters here. Okay? Since it only asks for volume, let's just leave it in there. And so what I end up with is an 81.5 milliliters of hydrochloric acid to neutralize it all. Now let's replace it with sulfuric acid instead. We're going to say the same strength. So this side stays the same. One hydroxide of a 0.350 molar, and it is 25 milliliters. Okay, on this side, I'm still solving for my milliliters. Okay, it is still going to be a 0.100 molar. But this time, since it's sulfuric acid, I have two hydrogens to play. And so what ends up happening is I end up with 43.8 milliliters. Notice I don't need as much acid if I have more hydrogens to play with. Okay, in fact, I need half. So it's pretty straightforward with this in terms of the math, and so we just kind of keep on going through the examples. Visualizing what's going on with this is going to be key. All right, so in this problem, we're going to be seeing that I'm going to be working with, let me switch over to this. I'm going to be switching over, and now we're going to be putting in, to this particular problem, I have nitric acid, and I have potassium hydroxide. Okay, so in an experiment we have 28 milliliters of 0.250 molar nitric acid, and look, we only have one hydrogen. I have 53 milliliters of the 0.320 molar, and I have one hydroxide. Oh, wait a minute. We're mixing those together, aren't we? I want to calculate the amount of water formed in the reaction and calculate the concentration. Well, notice I'm not asking how much in there. There is no question there. I'm taking a look at all this information. This is my acid side, and this is my base side. What is this question asking? This question is asking how much water will be formed. That's a stoichiometry problem. Okay, so let's take a look, and it also asks about the hydrogen or hydroxide in excess. So I have nitric acid, I have potassium hydroxide. It's going to be a precipitate reaction, kind of behave that way. And what I see is I'm going to end up with water as HOH, and I'm going to get potassium nitrate. Okay, so the question is, how much of each do I have? Okay, so here's the key. They say that I've got this much of my acid. Here's its strength. Okay, so here's my acid. It is a 0.250 molar. That means I have that many moles per liter. But I don't have a liter. I have 28 milliliters. That's a 0.028 liters of solution. And so what do I end up with? And the acid that I'm working with here is going to be my nitric. I have 0.028 liters with it. And notice with this, I have one nitric acid and 1 mole of water. Okay, so if I keep going with this, this is my nitric acid, 1 mole, because that's what I've got for units, 1 mole of my nitric acid to 1 mole of water. Okay, so what I end up with in this case is going to be 0.0070 moles of water. Okay, now let's do the same thing with my base. And let's follow that part. Okay, I see that I have 0.320 molar, and that base, again, is going to be potassium hydroxide. But that's molar, so that's 1 liter. And how much do I have? I have 0.053 liters. Now, since it's potassium hydroxide, notice I have one of those as well to balance it all out. So I have 1 mole of my potassium hydroxide to 1 mole of water. What I end up with, if it was up to the potassium hydroxide, is 0.0170 moles of water. Who did I run out of? I ran out of this. Here's my limiting reagent. Okay, so the question is, now how much is left over? Okay, how much hydroxide or hydrogen is left over, and I have excess of my potassium hydroxide. So remember how we do these problems. I take the difference between these two, I subtract the two from each other, and I see that I end up with 0.0070 moles of water difference. If I solve my water back, and that's going to be 1 mole of water, and that's 18 grams. So I can figure out how many grams of water. I guess I was asked that question first. I end up with 0.126 grams of water. Okay, so that answered that first part, 0.126. Now the second one is asking about how much excess remains. So if I subtract those two now, I end up with a difference of 0.0100 moles of hydroxide different. Okay, of that water difference. If I solve that back, I end up going a 0.028 liters of nitric plus my 0.053 liters of potassium hydroxide. That gives me a 0.12 moles of hydroxide remaining. Okay, so just pretty straightforward, following those things along the way. Now, other things that we can do with the with acids and bases, we can carry out an experiment to standardize and figure. When we mean standardize, it means that we're trying to figure out just how strong this thing is, determine the exact concentration of sodium hydroxide. Okay, so I'm going to do this and mass out 1.3009 grams of potassium hydrogen phthalate, KHP, and I give you the molar mass, and there is one acidic, has one acidic hydrogen to donate, has one hydrogen to play with. Okay, so in this, in all of this reading, what we're describing is that I have sodium hydroxide plus my KHP, C8H4O4, and that's going to break down into sodium ion plus hydroxide ion. And so what we'll get out of all of this thing is we're going to get potassium with my HC8H4O4 negative. Okay, so that the net ionic equation out of all of this, we can get rid of our spectators. I end up with this as my net ionic. All right, I end up with HC8H4O4 negative plus my hydroxide. That's going to give me my water and my C8H4O4 negative 2. Okay, so that gets rid of all these things as spectator ion and so on. So now let's do our math. Okay, they tell us the mass that we've got in here. We've got 1.3009 grams. Okay, so 1.3009 grams of my K, or my H, I should say, C8H4O4 with a negative. I'm going to convert that into moles, 204.22 grams of KHP to moles of KHP. And so I end up, oh, and I see within this 1 mole of KHP will give me 1 mole of hydroxide, won't it? So then I can convert that into my hydroxides, and so I get 0.006371 moles of hydroxides. And then I can put it into my molarity equation, because remember, molarity is moles over liters, so molarity equals 0.006371 moles of hydroxide, and I have a volume that I used of 0.04120 liters. I end up with a strength of 0.155 molar sodium hydroxide. Okay, just do a net ionic equation with it and pull it apart that way. Not too bad. Last problem. This is it. This is the last thing that we're going to be taking a look at with this chapter. We see that we're going to be taking a look at the experiment to standard. Oops, this one we've already done. An environmental chemist then used this problem to take a look at the effluent, the released waste material out of everything. Okay, so with this we see the balanced equation. We're taking a look and we're taking carbon tetrachloride and benzoic acid. It is a weak acid, which means that it's not going to be giving up many of the hydrogen ions. Okay, and we're going to be using sodium hydroxide for neutralization. So once again, I'll do my equation up here. I'm taking sodium hydroxide and I'm going to be mixing it with my benzoic acid. So it's HC7H5O2. I'm going to get sodiums released, I'm going to get hydroxides released, and I'm going to get some of these HC7H5O2 with a negative. Okay? Now, taking a look and doing a net ionic equation from all of this, I end up as my net ionic equation, I'm going to get hydroxide and my benzoic acid is HC7H5O2. I'm going to get water off of this, HOH, and I'm going to get this polyatomic C7H5O2, the negative. Now, in the whole problem, it's asking about the hydroxides in here. I have, with this, I have 0.1546 molar, and I have 10 10.59 milliliters. I'm looking for this, okay, just so you don't get lost in everything. So let's go ahead and do the math. I have 0.1546 molar. That equals 0.1546 moles per liter, doesn't it? But I don't have a liter that says that I have 10.59 milliliters. So that gives me a 0.01059 liters. Okay, now that's of my hydroxide. In my balanced equation, I see that I have 1 mole of hydroxide for every mole of my acid. And that acid is HC7H5O2. The reason I include that in there is because then I can figure out the grams. 1 mole of my acid, they tell me, has a mass of 122.12 grams of acid. And so that gives me 0.1999 grams of my acid. Okay, now the question is asking the mass percent of benzoic acid in the original sample. Now remember what mass percent is. Mass percent is grams of the piece divided by grams of the entire thing. So I had this many grams of the acid, and how much effluent did I have? I had 0.315 grams of the effluent, times 100% to give me my percent distribution, okay, mass percent. So that gives me a mass percent of 56.82%. Okay, what does that tell me? That effluent, that stuff that I'm being basically released as waste material, 56, almost 57% of it is benzoic acid. Okay, so just doing a couple problems with that, seeing how things are going, see how much aqueous solution is going to be required to neutralize those things and everything else. I'm just converting it to figure out the strength of the acid, if it's a weak acid or a weak base in there. Okay, that's all that we need to be able to do for this particular chapter. And notice that with the we started this unit with the different precipitate reactions and doing some stoichiometry with it. We end with the acids and bases that way too. We do some titrations. We do some things by basically figuring out how much was added in there. That should get you through all these problems. We're going to be getting into some a couple labs with this and put it into action. Good luck.